So when studying the natural world and even systems that we've engineered ourselves, it's apparently obvious that we will bump into at some stage the phenomenon of emergent synchronization. So on this channel I've showcased some projects, including this network of oscillators here, which I've called Feynman's fireflies, for the reason being that it actually incorporates a modified version of the firefly algorithm, metaheuristic technique, to display emergent adaptive behavior as well as synchronization. But some of the phenomena that can be kind of emerged from running these systems of oscillators that are coupled and display synchronization is that they display some very uncannily aspects of quantum physics, namely that the behavior of networks appears to be directed with a kind of a phase space interpretation. And what I mean by this is that one can actually plot the time evolution of this system in phase space and show that the classical synchronization in networks of oscillators, such as I showcase here, can be very, very similarly simulated with quantum systems, even incorporating some software that is used for emulating quantum evolution with the generation of such characteristics such as Wigner function and Sumi Q function, and so on. So in order to do this, of course, requires a bit of a multifaceted approach. One approach that I explored previously and showcased here was the utilization of actual physical oscillators, in this case engineered using microcontrollers, and then showcasing how the synchronization can be emergent and, of course, as shown here, disturbed and create a discontinuity in the steady state, as it were, to bring it to a new energy level and to actually showcase and characterize its behavior. And using Python, I've been able to actually analyze this video, because the interesting thing is that even though these oscillators are programmed to couple together, the actual behavior of them is non-programmed. It would actually require an infinite amount of code on each microcontroller to actually display this emergent adaptive behavior. So actually, when the system is run, one can do analysis of the actual video content itself and actually detect the number of instances that the beacon in this case is flashing. So this video shows the actual raw footage, but by doing essentially a ring detection and with a color basically filter, a digital mask that's only detecting the blue, one can actually showcase or plot the evolution of this system. And from a complex systems point of view, it's quite interesting. One can actually begin to look for discontinuities, but also what are called chimera states between the instances of discontinuous coupling and continuous coupling towards the point of synchronization. So if I stop the file here, I can actually plot a figure. Every time the beacon is found, it plots a PNG file, and one can actually see by kind of showcasing the time evolution of the system that there are regions of synchronization where the blue value is high and regions where it falls off, and it begins to enter a state where sort of the small oscillations begin to behave with the same frequency as the larger oscillations, and this kind of indicates to me that there's some chimera state forming in this emergent system. So what about quantum systems? Well, one can actually simulate quantum systems in Python using a series of libraries. One thing I should showcase is that there is, of course, this one called the Q-tip library, which you can set the Hilbert space size and the number of nodes, if you like, or the number of particles that are coupled in a cavity. That is to say, the number of particles in this case would be entangled, displaying quantum entanglement. So that's the main link. So by running the simulation, the main, if you like, benchmark that we want to find from these simulations in QTIP is we want to reconstruct the Wigner function to show essentially how steady the Wigner function is over the course of time. That's the main thing that we're looking at in terms of time evolution in the case of quantum states. So we have an initial state with its own Wigner function and some displaced state, and then the time evolution will show that the Wigner function actually begins to become more chaotic over time as the states move away from the initial state and begin to enter their steady state, but also display this sort of chimera of being in sync, being entangled, and being discontinuously coupled with various statistics to show the degree of broadening in the counting statistics. And it is interesting that you can also plot these as a Hinton plot. The plot isn't showing very well here, but if I perhaps move the bar a little bit, I can show the plot a little bit better. The Hinton plot of the density matrix. So density matrix can be plotted sort of analogously to the way neural networks can actually be plotted as well. And the similarity is actually not been lost on the scientists, physicists that are working in this space at the moment, trying to model quantum entangled networks as effectively complex systems, sort of analogous to neural networks. And this actually brings me to another library in Python, which is very useful for simulation and sort of displays a good chunk of the gist of what I'm talking about, the way in which one can actually model these systems as systems of oscillators that are coupled. And one figure that has been huge in this research for the last couple of years has been the utilization of the famous Kuramoto model of oscillators. So Kuramoto oscillators are effectively like pendula, or even in the case of quantum systems, quantum harmonic oscillators, which can be modeled as a graph-like structure. I might have to reset the kernel to show you more closely what I mean. But this suite of codes I can actually provide in my GitHub page here. It's been a project that I've been working on for a while. Basically a suite of software code in Python that can display this emergent behavior of synchronization in a quantum context. So the code I have here has been partially written by a scientist, mathematician, and computer scientist Hiroki Sayama in his book on complex systems. And I've been trying to bridge it with QTIP, this quantum simulation software in Python. And some interesting kind of conclusions have been made with this, that in fact quantum systems are similar to classical networks, and that they can both be treated with graph network theory. So here we have a graph, a directional acyclic graph, which is made up of a system of Kuramoto oscillators, which are effectively, in this case, been coded to behave like quantum oscillators. And the graph is directionally acyclic from the source node to the network, because entanglement effectively behaves as a one-way street. It has a sort of an entropic arrow of time. So if I run this simulation, eventually it will actually begin to display synchronization, where all of the nodes are being mapped as the same color in this case in the graph, but also in the phase space plot here, you can see the individual oscillators moving towards a synchronization, a one kind of supernode that's moving along the cavity, moving along in phase space as it evolves, as the state evolves over time. So you can see here there's two kind of regions of stability that are forming, and these could be considered chimera states, sort of similar to the regions of stability that have formed in this graph here, which is plotting the network of oscillators displaying the firefly algorithm. So it is very interesting to me that this sort of forms a bridge, tentative bridge between complex quantum networks and classical metaheuristic synchronization. And this is something that I have written about on my blog a few years ago. It was sort of a conclusion that I came to intuitively by looking at some of the mathematics of the path integral formalism in quantum mechanics, the path integral interpretation of quantum mechanics. So it is interesting that time evolution of synchronization from a unsynchronized to a synchronized state can evolve over time, passing through a threshold here. If I show you the article, and you can represent this mathematically as effectively a field, a signaling field, a scalar field, which undergoes some activation function with weights associated to it based on the network with a random probabilistic term, sort of keeping the region of interest out of sort of entering into traps of local minima or global minima. And the p-send is quantized; it's quantized element of signaling, of the signaling field. And using the path integral formalism, one can actually interpret the system as a sort of a Lagrangian of momentum in momentum space, with the abbreviated action being the integral of this p-send as a function of as a derivative of time. And this can kind of then, the frequency of signaling can be itself an oscillation in phase space. So one can actually model these systems using the path integral formalism. And this is a conclusion that's sort of been adopted by others as this research has continued since 2016. And one can actually plot using dynamical time warping the degree of synchronization between, say, two nodes or two quantum cavities, and this leads to a nice neural network interpretation of the system as a whole, with an input signaling and in some configuration space that's synchronized, leading to an output class. And the main motivation for doing this is to see if I can model the structure of these things, these systems, as it were, as Boltzmann machines, effectively. So the concept of Boltzmann machine is effectively a system of coupled fermions that one can kind of model as a whole system of density matrices. So the concept of Boltzmann machine kind of leads me to conclude that a lot of these systems that display discontinuous path coupling and metaheuristic synchronization can be treated with a quantum mechanical approach. There's nothing kind of, so to speak, taboo about treating Boltzmann machines, which are natural systems, or treating effectively engineered systems of oscillators as quantum mechanical, basically Boltzmann machines, as it were. And this kind of has led me to an interesting conclusion that what we take for as something special about these systems, these quantum systems engineered using things like low temperature superconductors, entangled systems of nonlinear optics, polarization entanglement, and so on, which I'm working with as well simultaneously in an optics lab. There's nothing particularly special about these systems. I mean, one could pose the question, Where does synchronization, where does entanglement end from the microscopic to the macroscopic, and synchronization begin? Classical, that is to say, classical synchronization, or to put another way, where does synchronization, when we scale down, if we were to shrink this circuit, say, down to the scale of atoms, or replicate it with atoms, or light particles in a circuit, where does synchronization stop and entanglement begin, quantum entanglement? And that's led me to the conclusion that there's nothing particularly special about entanglement if we actually look at it through the lens of metaheuristic synchronization, which is Kuromoto's famous model here, to actually begin to really model quantum emergent behavior. And that kind of leads very nicely into this phenomenon of quantum chaos, which is something I displayed, showcased on a video on this channel a few years ago. But quantum chaos may very well be almost identical to classical chaos under certain constraints. So my hope to kind of continue bridging these two fields together, the fields of classical and quantum network theory, but also more interestingly, the field of quantum and classical chaos. And I do believe, do have confidence that the study of these metaheuristic systems it could be the key. So I really do hope to be showcasing more of this research into the future, and with the intent of actually building another one of these devices to really show proof positive that these can be treated almost analogously to quantum networks themselves, made with such kind of exotic objects as entangled photons or coupled even quantum computers. So thanks very much for watching this video. It's perhaps a little bit abstract, but I really do think that studying the complex systems can actually lead to more and more bridges, hopefully in the future, between classical network theory and this emergent field of quantum network theory, and to kind of take some of the spookiness out of this word quantum, which has obviously been thrown around a lot, describing what seems to be new phenomena, but really to me seems to be describing variations on a theme that has been explored previously in the field of classical network theory and classical synchronization, with, of course, big contributions made by Kuromoto. So thanks very much for watching, and I definitely hope to showcase more about my own projects and contributions, and perhaps doing some literature review on this very interesting and exciting subject in the near future.